Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 3 of 4 on the topic of simple linear regression, and we'll discuss checking model assumptions. Let's get started. Let's revisit the assumptions that we made in building our regression model. The first is that the relationship between our variables is linear. The second is that the variance of the residuals is constant. The third is that the distribution of the residuals is normal. Finally, the fourth assumption is that the errors are independent. Not all these assumptions are equally important, nor have equal impacts on the validity of our model. There are 3 major consequences to violating the assumptions we made. First and foremost is that our model can end up being systematically wrong, that is, biased in one direction or another. This goes for the estimates of the intercept and coefficient, as well as the residual variance. The other 2 consequences affect model confidence and prediction intervals, but also tests of significance for the model as well. In some cases, the impact of these violations is pretty obvious. In the plot on the right, the data are clearly not linear, so any estimate based on the linear model is going to be wrong, especially when used outside the range of the data. However, it's not always this obvious. Luckily, there are tools that make it simple to check our assumptions. 3 of the 4 assumptions can be straightforward to fix. With the 4th assumption, which is the independence of errors, it's a bit more challenging. Let's look at a set of tools provided by default in R that let us check these assumptions. This plot of residuals versus fitted values helps us check for linearity. Any systematic pattern that appears in this plot is a sign that there's a deviation from linearity in the data. Each point is plotted as the fitted value on the x-axis and the residual for that fit on the y-axis. The red line is a smoothing line meant to make patterns easier to see. This plot for a model with good linearity will show a random scatter of points around the value y equals 0 with no trend in the points. The red line will be very close to the y equals 0 line. In this case, we see that there's curvature in these points, highlighted by the upward curvature of the red line. This systematic pattern is a sign that these data are probably not linear. When this occurs, the first thing we try to do is transform the data. Transformations involve using a monotone function like square root, logarithm, and so on the variable, and then using the transformed variable in the regression. Recall the normal quantile-quantile plot from exploratory data analysis. A normal quantile-quantile, or QQ plot, helps us identify if the residuals are normal or not. Data with a normal distribution will fall neatly along the dotted line in the plot. Non-normal data will deviate in any number of ways, as we saw in the discussion in exploratory data analysis. These data seem to behave well enough within about 1.5 to 2 standard deviations in the mean, but then have curling in the tails that seem to indicate that the residuals have heavier tails than the normal distribution. There are typically 2 options for dealing with non-normal residuals. The first and preferred option is to take transformations in the variable so that it becomes normally distributed, and then continue on with simple linear regression. If this can't solve the problem, often the solution is to use a more robust method, like generalized linear models, which is beyond the scope of this discussion. The scale location plot is one way to identify if the residual variance is constant with respect to x. This uses a transformation of the residuals plotted against the fitted values to help identify if the variance is changing. It's shown with a red smoothing line to help see patterns. The key here is to see if the red line is increasing. No pattern would be indicated by a relatively flat red line. This example shows potentially increasing variance towards the right side as shown by the slope of the red line. Another way to look at the constant variance assumption is to plot the residuals against the x values and to check the pattern. Non-constant variance appears as an increasing scatter in the points as the x variable increases. This often results in a plot like this where the shape of the residuals cloud is like a cone or a sideways parabola. I added in the red lines so you can see the general shape that indicates that there's a problem. The increasing spread on this plot is the same as the upward slope line on the last plot. When the residuals aren't constant, we have the same options as when the residuals aren't normal. First, we try transformations of the x, y, or both variables and see if the residual behavior improves. If transformations can't fix the problem, then we must turn to heavier machinery like generalized linear models. Another tool from exploratory data analysis we can use to check our regression is the run sequence plot. Recall that we can create a run sequence plot simply by plotting the residuals in the order they were observed. The x value is just the index. Any systematic pattern or trend in the run sequence plot is an indication that the residuals may not be independent. In this case, there's a small systematic pattern, like a small wave, in the first quarter of the plot. It's more likely that this is due to the nonlinearity we saw in the residuals versus fitted plot than it is due to dependence. We can also use the lag plot from exploratory data analysis to evaluate independence. Recall that you can create a lag plot by taking a sequence of values and plotting it against the shifted values. In other words, plot x1 versus x2, x2 versus x3, x3 versus x4, and so on. If the points cluster along the diagonal or look linear, then there's probably some dependency. If there's more of a scattershot cloud like this, then there's not strong evidence for dependence. When the residuals are dependent, the solution isn't easy. Often this involves using a much more complex model in order to capture the serial correlation. Such models are beyond the scope of this discussion. Leverage and influence aren't so much of a check of assumptions as they are a model quality question. Data with an extreme x or y, or x and y values, can have disproportionate influence on a regression. This typically happens when an observation is extreme in x and or y and doesn't follow the pattern of the remainder of the points. Least squares estimation is not robust to this situation and will attempt to fit the line through that observation because it's influential. An observation is said to have high leverage if it's far away from all of the other points. However, if it follows the general trend of the other points, it may have high leverage but low influence. That is, removing it would have only a small effect on the model results. However, as in this case, the point is high leverage and also influential. The result would change vastly if the extreme point were removed. It's important to identify these values and treat them appropriately because they can make or break your entire analysis. You don't want one influential observation making up your entire model. One additional diagnostic worth discussing is a leverage plot. The least squares estimates are not resistant to big outliers, and they can have a disproportionate influence on the result of the regression. The leverage plot is created by plotting a data point's leverage, which is its distance from the rest of the data, and also its residual value. The combination of a large leverage and a large residual means a large influence. Contours of constant influence, measured by a metric called Cook's distance, are shown in dotted red. Values worth checking have a Cook's distance that's much larger than the others. In this case, we have a few observations with larger Cook's distances, but the top two have a value of about 0.5, and there are others with values close to that, which is less concerning. If you identify influential observations, you can try the regression without the point included and see how much the result changes. If it doesn't change significantly, then there isn't likely to be a problem. If it does change significantly, you might need to consider changing the structure of your model or diving into the problematic observation a little bit more. In this video, we discussed checking model assumptions. Two key points to take away from this video are: we have a responsibility to check that our linear model does not violate the 4 key regression assumptions that we covered previously, and we also want to check to make sure that none of the data used to fit the model are concerningly influential. Thanks, and tune into the next video in this series on simple linear regression to learn about making predictions using linear models.